Welcome to this explainer. Listen, I am absolutely thrilled you're here today because we are tackling what is arguably one of the most crucial topics in analog layout design. If you're prepping for an interview in analog layout, AMS, PMIC, PLL, LDO, ADC, DAC, or even bandgap design, there's a super high probability you're going to be asked about current mirror layout. Today, we're going way beyond those theoretical schematics to explore the actual physical reality of analog layout on silicon. We're going to master matching, mismatch, and figure out exactly how to build genuinely resilient current mirrors.
Here is our roadmap for today. We'll start with the current mirror concept, look at the mismatch problem, cover core matching techniques, explain dummy devices, and wrap up with industry best practices.
All right, Section 1, the current mirror concept, copying perfection.
Let's start with the absolute basics of what we're actually trying to achieve on the chip. At its core, a current mirror is a circuit designed to do exactly what its name suggests. Perfectly copy one reference current, which we call Iref, into another branch, known as the output current, or Iout. Think of it kind of like a highly precise photocopy machine. If the original paper is perfect, the copy absolutely has to be perfect too. If our reference current is 10 microamps, the output needs to be exactly 10 microamps. If our multiplier is 2, well, the output should be 20 microamps. This exactness is literally the heartbeat of amplifiers, data converters, and power management ICs. Without it, the whole system just degrades. In theory, it's like an automatic system keeping two water tanks at the exact same level. If tank A, our reference, has exactly 10 liters, tank B has to be adjusted to hold exactly 10 liters.
Or think of it like a tea shop. You're the owner, and you prepare one perfect cup of tea. Now you tell your employee to make exactly the same tea. If the sugar, the milk, the tea powder, and the water are all absolutely identical, the taste of that output perfectly matches your reference. The current mirror works exactly like this. A reference transistor prepares the current, and the output transistor copies it. But it relies entirely on having completely identical ingredients.
Moving on to Section 2, the layout mismatch problem, the harsh silicon reality.
So, what happens when that perfect theoretical recipe meets the chaotic physical reality of chip fabrication? Well, the crucial point here is that a beautiful 10 microamp simulation on your computer screen can easily turn into a broken 11.2 microamp or even a severely deficient 9.4 microamp reality on fabricated silicon. Why does this happen? I mean, the schematic is flawless, right? The issue is layout mismatch. Perfect matching requires identical width, length, orientation, environment, stress, temperature, well, metal and current density. Any tiny difference in these physical traits, and your current changes drastically.
And honestly, this brilliantly illustrates why layout is just so staggeringly important. Nearly 80% of current mismatch comes entirely from layout-related effects if matching practices are ignored. 80%. The vast majority of your circuit success relies not on your schematic, but on how you physically draw it.
Because your chip is not a perfect vacuum. Every single fabricated chip is subjected to intense physical forces and variations. Let's dig a little deeper into exactly why this happens. First off, you have temperature gradients, where the left side of your chip might be 30 degrees Celsius and the right side 33 degrees, subtly altering carrier mobility. You have oxide thickness differences. If one transistor gets a slightly thicker oxide during growth, its current changes. Then we hit the advanced physical effects. Take the well proximity effect, or WPE. When energetic ions are implanted to form the well, some of them scatter off the photoresist edge and implant right into the active area, permanently changing the threshold voltage of devices closer to that edge. Then there's shallow trench isolation, STI, which physically compresses the silicon. This mechanical stress fundamentally alters transistor mobility depending on how close the device is to the trench. You've also got the length of diffusion, or LOD effect, which alters device behavior based on diffusion spacing. And of course, IR drop, where the voltage reaching one device differs just because of parasitic routing resistance. Every single one of these effects is actively fighting against your mirror's precision.
Let's look at Section 3, core matching techniques, fighting those gradients. To fight these physical variations, layout engineers have come up with some incredibly clever techniques. Notice how simple placement, just slapping device A next to device B, is absolutely the worst thing you can do. It's never preferred for precision analog circuits. Why? Well, imagine process variations, like temperature gradients, as sunlight hitting a room from left to right. The devices on the left get completely different exposure than the devices on the right. But if we use interdigitation, arranging them as AB, both devices share the same environment. They experience nearly identical sunlight, or process gradients, across the whole layout.
But for high-precision analog matching, we have an even better tool. It's arguably the most powerful industry secret to cancel out those linear process gradients. As the golden rule goes, common centroid is the most important matching technique.
By placing the geometric centers of matched devices at the exact same location, common centroid perfectly balances linear process gradients. Imagine four friends carrying a really heavy table. If they all stand on one side, obviously the table just tilts and falls. But if they stand equally around the center, the load perfectly balances out. Common centroid distributes the transistors around a central point, balancing the thermal and process load identically for both the reference and the output devices.
All right, Section 4, Dummy Devices Explained, Sacrificing the Edges.
Because even with a perfectly balanced center, the edges of our layout are still highly vulnerable to fabrication stress. This brings up a fascinating question. How exactly do we insulate the core layout from all that chaotic etching, chemical exposure, and physical stress happening right at the perimeter of our transistor array?
It's really elegant how this is solved. It's actually exactly like baking bread in an oven. The slices at the absolute ends of the loaf cook completely differently because they're exposed to way more direct ambient heat. So to make sure your important middle slices cook uniformly, you place extra unused bread slices at both ends. Those extra slices essentially act as shields. In silicon, we do the exact same thing. We place extra transistors at the edges to absorb those extreme manufacturing variations.
We call these shields dummy devices. Now, they aren't electrically active. Actually, their entire purpose is physical, to equalize silicon etching, equalize mechanical stress, and just drastically reduce those edge effects. By putting dummy devices on the outside, your active A and B devices on the inside experience a completely uniform, perfectly matched environment. The dummies basically sacrifice themselves so the active mirror can function perfectly.
Which brings us to Section 5, Best Practices and Pitfalls. Let's look at some real-world TSMC 28nm examples.
So how do we apply all this in cutting-edge fabrication nodes? Well, let's say you have a massive output device compared to your reference, like a ratio of 1 to 15. That might mean 4 fingers for the reference and a massive 60 fingers for the output. You absolutely cannot just draw one tiny block and one huge block. You have to split that 60-finger output device into equal unit fingers that exactly match the width and length of your reference fingers. Once everything is broken down into these identical modular units, use a hybrid symmetric arrangement. If a perfect common centroid is impossible to route just because of the massive size difference of 64 total fingers, use a high-quality interdigitated arrangement while maintaining strict core symmetry. You make sure the reference fingers are nested symmetrically right within the output fingers. And of course, you cap the entire array on both ends with multiple dummy fingers to guarantee identical source and drain environments for every single active unit finger.
Now, what's absolutely crucial to understand here is exactly what not to do. Some of the most common mistakes out there ruin matching instantly. Never use different orientations. Always keep them facing the exact same way so they experience similar layout-dependent effects like stress and implant angles. Instead of separate wells, use well sharing whenever the design rules permit it, since it improves environmental matching and saves you space. Instead of drawing one huge, wide transistor, use fingering to reduce gate resistance and keep the layout compact. And absolutely, under no circumstances, use asymmetric routing.
Listen, routing is just as important as the transistors themselves. You have to use symmetrical routing. That means the absolute same gate metal length, the identical source resistance, the exact same drain resistance, perfectly matching via counts, and the exact same metal layer. Every single detail matters here. Remember, unequal routing changes parasitic resistance and capacitance, and that causes massive current mismatch, even when your underlying transistor geometries are perfectly drawn.
If you're sitting in a layout interview for a top-tier semiconductor company anytime soon, you are almost certainly going to be asked to compare our two hero techniques. Which is better for matching, interdigitation or common centroid?
Well, here is your definitive answer. Interdigitation is highly effective for reducing local mismatch and simple gradients. And crucially, it's a lot easier to route. However, common centroid is mathematically superior and is always preferred for high-precision analog matching because it actively cancels first-order linear gradients by placing geometric centers at the exact same physical location. Though in reality, complex ratioed mirrors often require a hybrid of both of them, combined with those sacrificial dummy devices to get the job done perfectly.
Now, if you really want to deepen your mastery of these topics, I highly recommend checking out these industry standard texts. The Art of Analog Layout is incredible for practical applications like guard rings and dummy devices. CMO's Analog Circuit Design and Design of Analog CMOS Integrated Circuits are phenomenal for the underlying theory. And of course, you must always study your foundry's official PDK documents, like TSMC's for specific WPE, LOD, and spacing guidelines for advanced nodes. That is basically the ultimate golden rule.
We have covered a ton of ground in this explainer today, all the way from theoretical water tanks to interdigitation and common centroid layouts. It really leaves you wondering, doesn't it? If nearly 80% of current mismatch is determined entirely by layout and the true battle for precision is fought on the physical silicon rather than the schematic screen, how much of your next chip's failure, or success, is already hiding right there in the geometry of your design? Keep these techniques in mind, and I know your next layout will be a resounding success. Thanks so much for joining me.